Sorry for the abrupt cut-off on the previous session. I'm still a little bit unfamiliar with filming in high definition, so there are still teething problems, and it's possible this one might cut out suddenly as well. Okay, so continuing on with, we translated the third STI where the potential had a finite value, and instead of talking about the energies, we translated the problem into two expressions involving x, where x was defined as gamma times something or other. I don't remember from memory. Anyway, so the problem boiled down to drawing two sets of graphs along a common axis, a horizontal axis x, and you interpret x as just an angle, well it's just numbers. And you had one set of graphs, you were plotting for a given x, you were plotting the value of square root of gamma over x, all squared minus 1, and square root the whole thing. And the second set of graphs were the cotangent, in fact minus cotangent of x. Okay? And from the analysis of the previous session, where these graphs intersect, where they cut, for example here and here and here, the corresponding, the values of x where that happens, so here, here and here, they will give you the allowed energies. So from the values of particular value of x when they cut, when one of this square root thing cuts the cotangent, they correspond to the allowed energies, right? Okay, so looking at the graph, I mean, you can probably see, if you think a little bit about the cotangent, the nature of it, it'll look like this. We're not talking about negative values of this. Why? Well, this square root thing, this, is positive. Why is that? Well, why is that? So gamma over x squared, or gamma over x, is greater than 1. Why is that? Well, the definition of gamma over x is just this. It's square root of v naught over e. If you plug in the values. So gamma over x is equal to this square root v naught over e. But in this part of the analysis, we assumed that the energy here was less than v over e. Okay, so that means this is greater than 1. It has to be greater than 1. And if that's greater than 1, then gamma over x is greater than 1. And therefore this expression, the square root, is positive. Okay, so we don't have to worry about negative values of this. And since x is positive, because we're only considering the right-hand side, we were saving work by using the parity idea. So we're just dealing with the upper quarter of the space of the x square root thing space, right? So we don't have to worry about that quarter or that quarter or this quarter. Just this upper right, okay? The positive quadrant, if you like. Okay. Well, so you draw. So every pi, 3 pi, 4 pi, 5 pi, you can draw the cotangent values like this, the minus cotangent of x, and you'll get things like this, right? So that's fairly easy, and that's why we're using this x method, this approach, because it makes things easier in some ways. Now you can, for a given value of gamma, you can draw this graph, and you get these kinds of things. Now, the bigger your gamma becomes, the curves you get for this, they move out to the right more and more, and hence, given that you've got a cotangent curve going up, screaming up every pi, the larger your gamma is, these curves will sort of move out further and further, and hence they will cross more